In the first section of the chapter, we introduced perceptron. In the second section, we considered the add-line classifier. In this section, we'll consider a more advanced classifier called the logistic regression. The logistic regression classifier employs a specific activation function called the standard logistic sigmoid function, or simply the sigmoid function. The sigmoid function is defined as in this equation. You can plot this as in the figure, as the value is around 0 and approaching 1 as x increases. And it is a rotational symmetric. Okay. Here, 4 is derivative. You can have this one, but also the sigmoid function is the solution of this differential equation. Y prime is y times 1 minus y. Y at 0 is half. You can check it quite easily. And you can see here now its derivative as function times 1 minus the function. That's exactly this portion. Of course, at 0, the value is half. So the function is the solution of this differential equation. And also you can check quite easily this derivative is an even function. And also you can check this rotational symmetry. Sigma x plus sigma minus x is always 1 for every x. And also if you integrate the sigmoid function, you can reach this function, logarithm 1 plus e to the x, which is known as the soft plus function. And here, let's look at this green curve, which is the soft plus function. Now, if you consider this rectifier is defined in this way, taking maximum between the input and 0. So that is this blue curve. So for the value less than 0, we take 0 by taking maximum. Now that is called the rectifier. And this soft plus is a smooth approximation of this rectifier. So we call this one the soft plus, the integration of the logistic function. These three functions are very popular activation functions in machine learning. The logistic regression can be considered as a probabilistic model. The logistic regression maximizes the likelihood of parameter W. In reality, the algorithm is quite similar to add-line, only the difference is the activation function. If we try to see through this figure, in add-line, adaptive linear neuron, the net input is passing identity activation, which means that we are using the net input and we measure the difference from the label, and difference will be used to update the weights, the parameters, and that's the algorithm. Now for logistic regression, now for net input, we apply this sigmoid function for activation, and the output, the activity value, will be used to measure the difference from the label and the difference will be used to update the weight. So only the difference is this activation function. One is using the identity function, and the other one uses the logistic regression. And once the predicted value comes out, then the prediction is interpreted as the probability. Anyway, the value is between 0 and 1, and so we can consider the output as the probability of a particular sample belonging to the class 1. So we can write in this way, probability for the sample to be 1, class 1, and for given the point and under the W, the parameter. Now we'll see a little bit more about activation functions. Perceptron uses the thresholding technique, and Adeline adopts the identity function for its activation, while logistic regression uses the sigmoid function. Logistic regression is quite popular, particularly in medicine, because its probability for some disease, the output will give doctors certain probability of the disease, and based on the observation, and the doctors can understand the probability of a certain disease. The nonlinear activation function is incorporated in order to keep the net input restricted to a certain limit. Along with the sigmoid function, the output activated value must be between 0 and 1. So it is in the restricted the limit, and so that we can handle the quantities much more effectively. And also, it adds a certain nonlinearity, and that is also quite beneficial when the data set is noisy. And these classifiers are finding a separator, for example, 2 classes data set, and the classifier will try to find this separator. And now once it is noisy, and then for some points, the net input will have a value very large or very small, depending on your choice of labels, and so that the algorithm may have some oscillations during the iteration. By using this activation, you can stabilize the convergence of iteration. So it is really beneficial. Adding nonlinearity is really very positive point when you choose really good activation functions. Okay, here we begin a derivation of the logistic cost function. We assume that the individual samples in our data set are independent of one another. Then we can define the likelihood L as in this equation. So it is, for example, now active value, and along with here the for each one, now we can consider some probability, and the product becomes the likelihood, and we try to maximize this likelihood. For class 0, class 1, we have that, for example, and so that the value will be 1 for class 0, now this value will be around 1. Okay, for class 1, this will be around 1. And for class 0, the value will be around 1. So that along with this product, we can define likelihood and maximize. However, once we try to deal with this one, that the power and the quantities are small, so that we may have some underflow in the computation. So rather than dealing with this function, we may consider log likelihood. Then power becomes a multiplication, and this multiplication becomes addition. So we can write in this way. We have to maximize this log likelihood rather than maximization by multiplying negative. We can minimize. That's the final cost function. Here we have the algorithm, logistic regression learning. From the data set, we have to learn weights and the bias. Now, activation function is here the logistic sigmoid function, and cost function is the maximization of the likelihood, in fact, log likelihood, which is the same as equivalent to minimizing this logistic cost function. Here we multiply the -1, here minus and minus over there. Okay, so we try to minimize this objective function. That's the logistic regression cost function. Now, if we try to use the gradient descent method, we have to compute the gradient. So for this function, now it's easy to get the gradient. Here, we will not go to the detail, but you can check it quite easily. Now, first we try to make a WJ directional derivative. Okay, quite easy to get that one. Okay, let's see over there. Here, this one. Okay, phi z. Okay, phi z. That one is the same as phi, and we consider detail. Then that is W1 x1 plus W2 x2 plus the last one is WD xd and plus b. Right? So phi z is given in this way. So once you try to get derivative, then now this is constant, and here logarithm by using chain rule, and that will go to the bottom and is derivative on the top. So here we see derivative, and with respect to W0, and this go down, and for the second component is the same. Now we are using, for that one, we are using this identity. Here the derivative can be written as the sigma x times 1 minus sigma x. We'll use this identity to simplify. Then we reach at here, and in factor format, we can write in this way. For b derivative, again, we can get that one. So in gradient descent learning, minus gradient scaled by eta will be used for the correction vector. So we reach at this one. So that's the algorithm for logistic regression incorporating gradient descent method. The above formulation is really quite similar to that of add line. Only the difference is now this activation function. Now we are using a sigmoid function, but in add line we are using the identity function. Okay, that's the end of the section. Thank you.